talk, who's a professor.
It's a special conference for me because it's the first one I ever went to as a student in 2003 in Brisbane. And you never forget your first conference ever. So it's extra special to be here. So thank you for inviting me. All right, so I'm not going to talk to you about data sharing, FAIR principles, assuming all of that has been discussed. What I'll do is stretch your imagination in a slightly different direction. That how are we going to make predictive models useful in practice? Now, modeling could be a lot of things. One of our speakers is going to talk about, building physiological models, and there might be other kinds. I'm going to take a slightly narrower view just for the sake of simplicity and focus on models that are used in clinical practice. And that just happens to be the case because of what I do at my institution. All right, so let's begin with acknowledging the right people first. This is the diverse team that makes happen what I'm going to share with you today. The content today is practically everyone has had a particular sort of contribution to it, so I'm not going to highlight specific people. And obviously grateful for funding from the NIH, 2 institutions currently and a couple in the past to keep all of this going. All right, so this is sort of the punchline. This is a figure 4 directly from a paper that's underneath here at the URL. And the title for the paper is exactly what the talk is: a framework for making predictive models useful in practice. And just no need to read the text on here. Just remember the 4 colors. I'm going to keep using that color coding. And we'll just walk through the different steps: blue, yellow, green, and red, using one very specific example. And all of this is learned doing multiple models, but I'm going to use just one in the interest of simplicity and communication in a distributed environment. Okay, so the use case we'll be looking at is we want to improve advanced care planning using a predictive model. So advanced care planning, as some of you might know, is a repertoire of tools mostly involving conversation around goals of care for patients who are quite sick. In the US, the short way to describe it is that it's offered too little, too late. So in understanding this use case, on the left is a little plot that is showing on the x-axis the number of days before someone dies. And on the y-axis is the percentage of individuals who've had a conversation documented about advanced care planning. Now, as you can see, the majority of the conversations happen 30 days before somebody passes away, which is not ideal. A lot of individuals' final wishes are not honored. The way they want to spend time does not get done properly. And there's lots of research around this. But the problem that we've honed in on is that we do these things too late and too little, in the sense that if you see this particular plot and ask how many individuals even got the conversation, the numbers are in the 8 to 10% range. Okay. Then we ask, if someone had a model, if there was some magic way to say, Nigam is going to die at this particular time, what will we do? So the workflow to administer this conversation for advanced care planning involves 21 steps, 7 handoffs, takes about 48 hours. And that's this thing on the right. I mean, all that's the point here is that once you have a prediction, what we do in response is usually complex. It's not one click. It's not like advertising. And even there, I mean, you need to have the person click and buy something and check out and so on. But here it's way more complex. Involves multiple humans, multiple decision points. And the thing that the model is going to automate is in that red box. And I'm using model as in a general form that it's a mathematical function linking certain inputs to outputs. And it could be a logistic regression to a deep neural net, but it's a functional form that maps inputs to outputs. So in this use case assessment, we basically try to build a thorough understanding of why are we predicting? And once we have a prediction, what are we going to do? And who is or who are the people that will take action? Based on that, we then sit and decide the model formulation, as in what is the learning task? So in this particular case, ideally, the task I would want to solve is to be able to say people who will benefit and not benefit, like go through the chart and label them as will benefit or will not benefit, or needs advanced care planning or do not need advanced care planning. Analogous to, say, taking an email and labeling it as spam or not spam. Now that's pretty intensive. We can't go through and label 10,000 cases that way because it takes a lot of time. So we do a little bit of bait and switch and we predict a surrogate event. In this case, the surrogate event is mortality. The assumption being that if somebody is likely to die, they will benefit from advanced care planning. Now, with the caveat that not every death can be predicted. Accidents are notoriously difficult to predict, or if not impossible. And not every person who is involved in that situation is a good candidate. So there's a little bit of caveat there. But it gives us a good way to get labels really fast. And on the image below just shows you the setup, that the label we're predicting is occurrence of an event between those two red arrows. Blue is the time at which we want to make the prediction, and the observation window is the duration of record we'd have to make the prediction. And it's a true prediction about something in the future and not a classification masquerading as a prediction. Often in this field, we see things like, oh, we looked at an X-ray and predict it's a pneumonia. Well, that's not really prediction. I mean, it's classification. In this phase is when we would have evaluated other models if they were available to us at that point in time. I'm just acknowledging a limitation that we could have done an evaluation of a particular vendor provided model, but we did not have access to it at that particular point. So that gets us to the blue phase. Think of it as diligence. What's the use case? Do I need to build a model? What's the model? What's the outcome? Can I reuse an existing one or whatnot? Then we get into the yellow phase, the development phase. And, you know, like most geeks, we also went a little bit over the top with this, ended up building multiple different models in predicting that label we just chatted about, the 3 to 12 month mortality. And then on the right-hand side, you see all of the different ones. The first ones is just a panel of gradient boosted models and a lasso. I'm showing you precision, recall, and calibration. In the middle is a deep neural net. The last one is for sort of calibrated predictions about time to event, just like you would do in a weather prediction. All of these were evaluated using held out test sets. The bullet points on screen are for the top two, the gradient boosted one, and then the lasso. We got a lot of press for the deep neural net. The one in practice is much simpler. It's the gradient boosted model. So this is fun. This is where a lot of effort typically focuses. This is where a lot of technical work gets done. Computer science papers get written, informatics papers get written, and so on. But then at the same time, we have to look at practical feasibility. And so I'm going to go back just a little bit. So remember this observation window just prior to the prediction date. In order to run or apply the model and run inference for a new patient, I need to get this whole observation window worth of data. And is it even practically feasible in the setup that someone is in? In this case, our workflow unfolds over 48 hours. So we got time. It's not a ICU sepsis kind of situation where you need to make predictions in minutes. And in the end, we ended up having to suck in 33 tables live from the health system. Those of you interact with the EHR data know that it's pretty messy and usually 24 to 48 hour delay before it gets into your data warehouse. A typical length of stay is about 4 days, and you can't just wait for 2 days for the data to arrive. So we had to do something much faster. And then the punchline here is that the data sizes were such that we needed 33 tables in order to build that entire prior longitudinal medical record. And then we had to sort of haggle and settle saying, we're going to get 7 in the morning, 7 tables, so that we can get a base prediction in place. And then we'll wait till the evening to get 26 other tables, mostly because of queuing and this kind of fun stuff in an IT org. None of this ever gets talked about. But if you need a prediction by 7 a.m. and you're not going to get your data till 4 p.m. in the evening, you're not going to be able to make the prediction, no matter how fancy your model is. And so these are the kinds of things I urge people to pay attention to. All right, so then we have the model, we have the data availability. Now we're designing the deployment. And so remember I told you we were using a surrogate label. Instead of will benefit, we're using mortality. So we did a prospective validation with human judgment that we're predicting this alternative outcome and then pretending that it's finding people who will benefit. Is that true? The second very important thing is to establish a baseline so that we know whether we're making a difference. So before we began, the heuristic in place that was used is if someone has 3 or more admissions to the hospital in the past year, we're going to flag them as a potential candidate that would have found 21% of the cases and still required some human to go through about 2.5 charts to confirm the true case. Then, because the responsive party in this case is a group of humans, we're kind of reliant on their ability to make time for the additional cases we're going to send their way. So we quantified the increased workload over a few days of hospital throughput, and turns out that would be increasing the work by about 69% in the internal medicine department. Now, if you're going to do that, ask somebody to do that much extra work, you better quantify the expected improvement. So in this case, if we maintained recall at the current status quo of 21%, we would cut the chart screening work in half. If the 2.5 cases worth of chart review was sustainable, we can improve recall to about 84% and find 4 times the more cases. And as you can imagine, most people went for the increased recall, given that they're already staffed for the work capacity. Then this is sort of the most novel part, that in asking the hardest questions, that given the costs of taking action, given the costs of inaction, given the cost of following up with a false positive, and the negative cost of missing somebody, all said and done, is there net utility? And you could quantify that in dollars, you could quantify that in number of hours saved, or in the increase in quality of life, whichever way you choose, it just has to be the same units. And the plot on the top, on the right-hand side, is essentially a receiver operator curve on which I've overlaid sort of 3 lines. The lowest one is that if we do nothing, and then that's this yellow dot here, and then we can just sort of extrapolate that what are other positions in the ROC plot, other positions in this plot of false positive versus true positive, where you would have equal net benefit in whatever units. Red is if we do something for all positive, and then blue is the farthest point on the receiver operator curve, just to convince ourselves that by using a model, we're going to be making better decisions than doing nothing or just following up with everybody. Then we ran a simulation, which I don't have on the plot here, to model that given the workflow with 48 hours and 21 steps and handoffs, those will fail at some point. And 10% of the time, your handoff fails, or some fraction of the time, the patient's family denies certain decisions. So if we simulate, say, 500 days of throughput, what is the effect of that on the net benefit? And then trade-offs among delivery factors, as in, do we have to follow up with that crazy 21-step workflow? Could we do something in the outpatient setting? And how does that affect our net benefit? And then the last one is another sort of non-standard one, which is on the right-hand side at the bottom, is on the x-axis is just the probability thresholds going from 1 to 0. So all the cases that are ranked. The blue boxes are the number of cases that had a certain probability level on the x-axis. And then on the y-axis is cumulative per patient utility accrued at that particular value. And so as we march down the list, take action on 8 patients, 1 patient, 8, 16, 19, 22, you can see that our utility is sort of tracking up for a while, and then it starts declining. Intuitively, like, it makes sense to follow up on your top predictions, but not follow up all the way to the list. That's also seen in this yellow, red, and blue lines. And that green rectangle is how far down the list we're going to get, given the capacity we have on hand. So what is the realized utility given work capacity? All right. Now that's all in silico. We've convinced ourselves this thing is useful. Now we put it in practice. And on the top here is monitoring the work system, which is the model and the corresponding workflow. And what we're seeing is as time goes on, what is the percentage of individuals of discharges from the hospital where we have documented ACP, the real goal that we're trying to measure. And red is when COVID started. So you can see we just got off the ground and boom, everything tanked, and then we're kind of getting back up. And then these dips in the middle are like, dog ate the homework kind of thing. Oh, the data feed failed today, and the predictions didn't go out, and all of that nonsense. And then finally is this price of using old data. Like as time goes on, things change. The way decisions are made changes. And we can't just keep using the exact same model. And this plot here, sort of the main thing to pay attention to here is the red dots. The red dots are those where if we used a model trained with 2010 data versus something trained at using 2017 data, we made a better decision with the 2017 model. So 6 years go by, and if you did not retrain the model, all of the red dots are the ones on whom you would do something wrong, as in you'd either miss them or you'd have a conversation with them. And either case, you'd be in either the false positive or false negative. All right. And then finally, we got to be honest. And once this is in practice, prospectively evaluate. Did we improve things for the better, or are we just doing a whole bunch of computation for not much to gain? And so this one is out in a Medium post. And then I'll close out with this one table that we then, once we did this work, we said, like, if someone wants to reproduce all of this, what is the community provided guidance for doing this? So the columns are the exact same stages I walked you through, the blue, yellow, green, and red. And then the rows are the different sort of suggestions or proclamations from the community about how thou shalt do this. And the color coding is based on, does the particular recommendation, which is in a row, give you exact instructions on how to do a particular step, or it basically says you need to, but doesn't really tell you how? That's the light colored cells. One thing is obvious. As a community, we don't pay much attention to utility assessment and deployment design. There's decent information on what shall you report for prospective eval, decent information on how shall we define the model, and sort of reasonable for model development. But you can see there's large gaps. And then there's no recommendation, no road that covers everything soup to nuts, which is also kind of interesting. And so there's major gaps in the existing recommendations, both horizontally and vertically. And then we did evaluate ethical concerns. I view them as cross-cutting, that goes across all stages. I don't have time to go into them in detail today. The point here is that there's this prediction algorithm, and then it affects computer scientists, patients, regulators, insurance companies, providers, and we interviewed stakeholders from multiple domains. And then there's a bunch of publications, and then I'll stop here and hand it back